Hello everyone. Let me place this window in a better place and we can get started. Alright. Just a few seconds, a little bit more. Woo. Let's see. That's me. Hello. Alright. Hello everyone and welcome to the Daily Space for Thursday, August 9th of 2018. I am your host, Dr. Andres Plazas. I'm back after a break. And as always, we're going to bring you a run-up of today's news from space and astronomy. So today I pick up three stories, two of them about the solar system and one about black holes. We all love black holes. So let me switch the screen here for our first story. There you go. Okay, I see everyone. Hello, DPI, Fenring, Uncle Bill, Honey, how are you? So the first story of today has to do with Jupiter color bands, and this is a story where scientists from Australia and the United States have used data to try to help solve the mystery underlying the color bands in Jupiter. So, as we know, of course, Jupiter is the largest planet in our solar system, and unlike the Earth, it does not have any solid surface. It's what we call a giant a gaseous giant planet, and it consists mostly of hydrogen and helium. And in all these pretty pictures from Jupiter, we can always see these jet streams that flow from west to east, all those bands in the atmosphere, and in a way they're similar to the Earth. But these are clouds of ammonia and in Jupiter outer atmosphere that are carried along by these jet streams, and that they form the color bands, as I just said. So the scientists in these studies, they mentioned that here on Earth we also have similar Earth jet streams, and they play a key role in the weather and the climate. But we still have a lot to learn about the atmosphere in Jupiter. And scientists have long debated how deep the jet streams reach beneath the surface of Jupiter and other gas giants. And so they have used data from Juno, from the NASA spacecraft Juno, and they have found out that these jet streams can reach as deep as 3,000 kilometers below Jupiter's clouds. And then they were wondering why do they stop? Why don't they keep going further into the planet? So, researchers from the United States, in particular from the Livermore National Laboratory, they mentioned that actually the particular detail that causes the jet stream to stop is that the gas in the interior of Jupiter is magnetized. So that's why they think that the jet streams they go as deep as they go, but they do not keep going deeper. So as I mentioned before, these jet streams and they have a huge impact on the weather and the climate of the Earth because they act as a barrier, a physical barrier, making it harder for air on either side of them to exchange properties such as heat and moisture and carbon. That's what happens on the Earth. Um, what happens on Jupiter is a little bit simpler, so to speak, because compared to the jet streams that we find on Jupiter, the ones on the Earth are a little bit wavy and irregular because we have features in the surface such as mountains and geographical features like this that can change this in the jet streams of the Earth. You don't find that in Jupiter, and that's why they are like a little bit simpler, as I said, so to speak, and they just go around the planet for in almost all the planet in a way that is different from the Earth. But yeah, so in this is a research that appeared in the Astrophysical Journal, and they do use, as I said, simulate. They use data from Juno and they use mathematical calculations to try to figure out how they actually work, how the jet streams and the atmosphere of Jupiter works. So yeah, that was an interesting news about Jupiter that I found and I wanted to share with you. And I also found another press release related to the formation of the solar system. And this is an interesting research from scientists from the Max Planck Institute for Radio Astronomy in Bonn, in Germany, where they are trying to figure out with simulations why do we observe these certain features in the outer solar system. So just backing up a little bit, we know the basic scenario for the formation of the solar system. So in general terms, the sun was born from a collapsing cloud of gas and dust, and then in the process, then you had this flat disk that was formed. And then from this disk, the large planets grew, and also the smaller objects like asteroids or dwarf planets. So given this formation and due to the flatness of the disk, then we would expect that the planets orbit in a single plane, unless something extraordinary happened afterwards. So this, when we look at the solar system nowadays, we actually see that everything seems according to this scenario, up to the orbit of Neptune, where everything seems okay, and most planets move from more or less circular orbits and the orbital inclinations are not too high. But when you go beyond Neptune, then things start to become a little bit messy. So these are the kind of different features that we were trying to explain. Like, for example, we have a dwarf planet like Sedna that has a very high inclination and a highly eccentric orbit, and is very far in the outside. That's not the only thing that it seems strange. When you add up all the mass of the objects beyond the orbit of Neptune, or what you call the cumulative mass of all the objects, this sum is actually about 3 orders of magnitude smaller than the rest of the mass of the planets of the solar system. And this is happening more or less at this same place, like after Neptune, and researchers said, okay, this might be a coincidence, but actually maybe not. I think this sounds like something weird that maybe we could explain with a single mechanism. So the researchers in this study, actually Dr. Susanne Falsner, from, as I said, from the Max Planck Institute in Germany, in Bonn, Germany, they suggest that maybe there was a star that was approaching the sun at an early stage, and this star created a perturbation that steals most of the outer material from the sun's protoplanetary disk. And actually, this, in addition of stealing this material that would account for the missing mass, it would also perturb the orbits of the other objects, and then would throw them into more inclined and eccentric orbits. So how do we do this? We actually don't have a solar system in our lab. As I said, it would be great if we have the universe in a lab, or the solar system in a lab, but we have computers, so we do simulations. And we know the dynamics of the solar system. We know the mathematical equations that govern the celestial mechanics of the solar system up to a certain age. If you go to a very, very large time, then the system becomes chaotic, but there are simulations that you can do, and that's exactly what they did in this research. And they said that the results that the best fit for today's outer solar system comes from a perturbing star which had about the same mass as the sun, or a little bit larger, or smaller, sorry, and like with a mass that is comparable to the sun, and flew past at approximately 3 times the distance of Neptune. So they said that in addition of explaining these two features, the researchers were also surprised that these simulations also give a natural explanation for other unexplained features of the solar system. One of them that they mention is the difference in mass between Neptune and Uranus, and the existence of different populations of Kuiper belt objects. And in the press release, the researchers explored. They mentioned that right now we're gathering more and more data for these trans-Neptunian objects, but the data is still scarce. So it is scarce. So it is still important to rely on these simulations and on these predictions. And there are a lot of options that we can explore. So, of course, as we have mentioned these times in daily space, in the end, we're gonna need more data to figure out what's actually happening. But in the meantime, we can have all these theories and we can make simulations and we can see if they make sense. Another important thing that they mention in the study is that this explanation for them is relatively simple and it's able to explain a lot of features. So it has a high predictive power. So this is attractive, when in science we usually want to look for simple explanations that can tell me about the most, they can explain the most observations as they can. We don't want to have one explanation for each observation. That's not what we want to have. So a final remark in this study is what is the likelihood for such an event to occur? So nowadays these types of flybys are even of hundreds of times more distance than the ones that they're talking about here. They're very rare. They would be very rare. However, the researchers they say that the stars like the sun they were typically born in a large groups of stars, so the space was more crowded. So the flybys actually are more likely to happen, and they were able to quantify this number to about a chance of 20 to 30% of experiencing a flyby, which is high, is relatively high. So of course, this is not a final proof that this stellar flyby caused all these messy features that we're talking about in the trans-Neptunian population, but it is a simple explanation that is backed up by the theory and by the simulations that they have done. And yes, in the end, we will need more data and see what's going on. So yes, and the final study that I wanted to share with you has to do with intermediate mass black holes. So we have mentioned in the past that we have different types of black holes. We have those that come from star collapses, and those are about the mass of those black holes are about 100 times less the mass of our sun, 100 times solar masses. Then we have also talked about the giant black hole at the center of the Milky Way, of galaxies such as the Milky Way, and those are called the supermassive black holes. But then in between, not naturally, we have something that we call intermediate mass black holes. It's a very large range of black holes in mass. It's about 100 times the mass of our sun up to 100,000 times the mass of our sun, so 10 to the 2 to 10 to the 5. And the interesting thing about this type of objects is that we actually are not sure about how they form, and we don't have like a direct evidence of their existence. We have some circumstantial evidence, and the a study that I'm going to present, that I'm going to show you guys today, has to do with using data from the Chandra X-ray Observatory in order to try to create a better census of this type of intermediate mass black holes. So in this study, they actually use data from, as I said, from Chandra, from the Cosmos Legacy Survey, to study dwarf galaxies. This is one of the interesting things that they have found. They were focusing on dwarf galaxies that contain about less than 1% of the amount of the mass in the stars, like the galaxy of the Milky Way. So hence, that's what they call dwarf galaxies. And they were able to identify these point-like source X-ray emissions, and that actually signal the presence of this type of black hole. And they mentioned that with this study, they might have found that the dwarf galaxies are actually a haven for these missing types of middleweight black holes. They didn't know that they might actually be so common in this type of dwarf galaxies. This type of galaxies are actually very hard to find, and they're very interesting to find because the current very interesting to study because the current theory of cosmology that we have predicts a larger amount of these dwarf galaxies than we have actually seen. But it could be that maybe just because they're very hard to find out, that we find a mismatch between the observations and the theory. But in this particular case, they use this type of dwarf galaxy to find this particular kind of black holes. And so the team in this study, they actually identified about 40 growing black holes in dwarf galaxies. About 12 of them are located at distance of more at very far distances of more than 5 billion light years, or even up to 10 billion light years. And the interesting thing is that in addition of using this subset of the Chandra data, they also used other type of subset of the using also data from the Sloan Digital Sky Survey, and they were able to find another set of dwarf galaxies that contain this type of black holes. But in this particular sample, the most distant intermediate mass black hole candidate is about 3 billion light years compared to the other sample that was about 5 or to 10 billion light years away. And so all in all, this is the largest sample of intermediate mass black holes ever found. That's what the researchers point out. And yeah, we want to actually use this type of black holes, or to first because we want to have a complete census of all the cosmic objects that are there, but also this may help us to explain how the very largest black holes are formed, the supermassive black holes that I was talking about at the beginning. How so? Because one leading explanation is that supermassive black holes grow over time from smaller black holes that are seeds containing about 100 times the mass of the sun, so intermediate black holes. And some of these seeds, they should merge to form intermediate mass black holes. So yeah, that's one explanation, but they say there are other explanations. For example, that they might form very quickly from the collapse of a giant cloud of gas with a mass that has hundreds of thousands of times the mass of the sun. So finding more about this type of intermediate black holes can help us actually understand more about those supermassive black holes that are millions, starting at 1 million times the mass of the sun, and you can find at the center of galaxies such as our own. All right, so those are the 3 stories that I wanted to share, and as usual, I'm looking forward to read your comments and see what you guys think. So let me go back and take a look at it to take any questions that you may have. Actually, maybe move the camera a little bit here. There you go. All right, so hello, Uncle Bill. Fenring, hello. So Hani has one question. Let me just open a little bit more the chat window here. So Hani is asking, would the magnetization cause another pattern in the deeper gas? That's a good question, and I don't have the answer for that question, but I will have to learn more about that. But I'm trying to think. Maybe I'm thinking about the sun, where you have a very prominent role of magnetic fields in the shape of the charged jet streams that they have. So depending if you have a jet stream of charged particles or something like that, I'm just trying to think of another type of patterns that would be caused. But in this particular study, they found that actually the magnetic field acted as a suppressing mechanism for the jets, so they don't go deeper than 3,000 kilometers. So I didn't check exactly the exact mechanism for that, and I would have to check, but that would be interesting. And then once we know the type of distribution of the magnetic field and how it's actually coupling to the gas, then we can have a better idea of if it could cause a different type of pattern, not only in the jet streams, but maybe in some other surrounding material. So, hello, Larry. You were finishing making breakfast. Awesome. Adamald, hello. So Hani asks us another question regarding Gaia. Could Gaia data be used to find stars that could have come near the sun in the last few million years? Um, I would say I'm not sure about that, but I would say yes, because you can measure very precisely the peculiar motion of the stars with Gaia. That's the point of the whole point of Gaia is to get a better map of stellar density and of their velocities. And once you know the peculiar motions of these stars, that you can start solving for their orbital elements and for the dynamics, and actually try to figure out what they were doing before, and then we're going using that as a starting conditions to see what they're going to actually do in the future. So Larry says test could too. Yes. Hello. So Dell1337. Hello. Hello, honey. Thank you for all your questions. Awesome. Were any of the black holes that were found by LIGO in the intermediate range? I remember people being surprised by their size for some reason. You're right, and I think they were not. I will have to check that, but I don't think, as far as I remember from one of the papers when I was reading, I don't think the mass of the black holes found in one of the first discoveries by LIGO were more than 100 solar masses. So, which that would be the definition for the intermediate mass black holes. So that's my recollection of the fact of when I read one of those papers in about it has been like there have been like three releases, but one of them having to do with electromagnetic counterparts. But the very first one they had to do with pure black hole binary mergers, and I don't think their mass surpassed that of um, the threshold to make it to an intermediate mass black hole. Um, could Dell1337, could black holes collide with other black holes to create larger ones? Yes, exactly. That's what when we talk about binary mergers, black holes mergers, and this is one of the type of black holes that was found by LIGO. And there are a lot of cool animations online, and I remember when the National Science Foundations gave the news, they have all these cool animations made by I believe by the group at Caltech, where you can see the simulation of how the two black holes merge together, and they start producing the perturbations in space-times that we can observe as gravitational waves. Honey. So Dell says you can just call me Dell if you want. All right, I'll call you Dell. Thank you. In general, I have trouble to reading all the names, but I give my best. Okay, I have another interesting question here. Could it just be easier to find intermediate black holes in dwarf galaxies? Maybe because they are not cluttered. Yes, that's one of the reasons why we want to study this type of data with Chandra, try to find more of these um, of these black holes, intermediate mass black holes that are in dwarf galaxies. So scientists also think that another environment to create intermediate mass black holes could be in globular clusters, when you actually find a lot of stars that can merge together and start producing this type of black holes. But and again, all this evidence is it's not definite, and I remember a few months or weeks talking about one of those news, and people were uh, analyzing data that was pointing to the fact that there might have been evidence for the formation of intermediate mass black holes in globular clusters. So now we're talking about dwarf galaxies, and which is exciting. It's in for us a surprise, but as we get to find more of these type of dwarf galaxies that are by themselves difficult to find, then we can learn more also about this other type of astrophysical objects. Um, do you see me? And then Phoenix says like, yes, you see me. That's great. Awesome. Things are working well with technology and the laws of physics. Um, Larry, is there a black hole closer than Cygnus X1? I don't know, actually. Larry, you always ask me very good questions, and I don't know. I could Google that. I would have to check that, but to be honest, I don't know. Does the sun have any jet streams? Yeah, doubt when actually I don't know exactly, but I remember. So in this particular news, actually, maybe I think I forgot to mention that, but one of the other reasons why it is interesting to study these jet streams in Jupiter and the role of the magnetic fields is because people actually don't observe this type of jet streams actually in the sun. And now um, I'm checking this. Yes, they actually the scientists mention they want to know how deep the jet streams reach beneath the surface of Jupiter and other gas giants, and why they do not appear in the interior of the sun. So yes, I guess they don't see them, and they wanna try to understand why so. So yes, do you guys have any other comments because or questions? Because soon we will have Dr. Pamela Gay with a special guest, which I think she earlier described as someone who does hipster science, I think. So, yes, I think if you guys don't have any more questions or any comments, maybe it's about time to hand the transmission over to Dr. Gay. And well, as usual, thank you so much for watching, and it's my pleasure always to be here with you at least once in a while and chat with you and have all these comments about all these interesting topics in science and astronomy. So this has been the Daily Space, and as you know, it's a production of CosmoQuest, created by the Astronomical Society of the Pacific. And as usual, please give us a follow, talk to your friends about us, put us on social media. That help us a lot, and please consider subscribing. That would be great. That would be awesome. And yes, as I mentioned, we are handing over the transmission to Dr. Gay for the learning space. And tomorrow, of course, don't forget to tune in for your daily space at 1 p.m. Eastern, 10 p.m. Pacific, and 6 p.m. London. All right, everyone. Adios. Bye bye.